Okay, morning everybody. I hope you're as glad to be here as I am. I really enjoyed wet, awful north of England. It's an amazing place, and I'm really looking forward to spending this week together. And we will be talking about this a lot today. And what I wanted to do now is to show you a bit what we have done and where we got to. It was, well, it has been an amazing program, and as it was just mentioned, driven by very fundamental questions that for me are super exciting, and I hope to show you that we made some important progress on those. So I thought I would not need to motivate thermodynamics at the nanoscale for the people here. Okay, I mean, I can do that if anybody wants to know more. But I thought that I would start basically showing one of the games that one of our students coded. It's a Maxwell Demon. It's a game. You can play it. It is highly addictive. So I would warn you against it. So you can play the demon. So you can open that partition and try to accumulate the hot particles, the red particles on one side and the cold particles in the other, and in apparent violation of the second law of thermodynamics. And as you know, it really is not. But it's a really fun game to play, and you can tell me how much did you lower your Shannon entropy in the process. All this to say that information plays a crucial role in thermodynamics, and what we wanted to understand is how do we think about even quantum information, and what would be the revised laws of thermodynamics and the revised role of information in thermodynamics in regimes where quantum effects are important and fluctuations cannot be averaged out. Okay, so what did we do? Something that I really liked about this program is that it gives us space to do experiments that are really difficult. These are really difficult experiments. And why? Well, because you can see different realizations of some of the experiments that had happened before the information as fuel program. Well, some a bit more recent here, but we need systems that are fairly complicated, because if you think about it, the most kind of standard thermodynamic system has heat baths, right? A working gas or fluid, a piston, and a battery, and in order to monitor this whole thermodynamic process, you need several elements, and all these have to come together in a system that supports quantum effects and that supports fluctuations that are not negligible. So this is not easy to put together in a system. And definitely not in the quantum regime. So there have been some, for example, single atom heat engines and a couple of Maxwell demons with superconducting qubits and other semiconductor platforms where there were some heat engines as well. But it was very few. Before this program, really, we had very few experiments that would basically test all the theoretical hypotheses that we have about thermodynamics in this new realm. What did we want to bring to this picture when we started the program? We wanted to bring the piston in, because so far, and real heat reservoirs, in the sense that many of these systems have reservoirs that were quantum, and therefore they didn't really act as real reservoirs, right? They had limits to it. And it was very hard to measure the work done by a system, because we had no way to probe it in a direct way. We had to always estimate it. So what we thought we would bring in is a piston. We needed a piston, and we thought we could do that. So we could integrate in different semiconductor platforms different mechanical resonators. I would be talking today mainly, not all the time, but mainly about these carbon nanotubes that are suspended and have a mechanical degree of freedom that you can think as a piston. So from there, we can measure directly the work done by the system. So this is what we thought we could bring in. But of course, we had to build a platform and understand what this moving part could tell us about thermodynamics and which hypotheses we could test. One of the first things we did was to try and understand the thermodynamic cost of timekeeping. What is this? So a clock is a machine, right? We just give it some resource, has some waste, and it does something for you. Measure time, yeah? So it does tick, tick. So that's what it does for you. And it was predicted that in a paper by our collaborators, which in fact are this group here, the this also information as fuel program. So this is another aspect that I hope to convey today, that these different groups, we have been working quite a lot together and managed to do quite exciting things. And basically, they've been thinking about these clocks and what would be the thermodynamic cost of actually keeping track of time, looking at clocks as machines. So what they had predicted is that in a quantum autonomous clock, if you want to make it more accurate, you have to pay more thermodynamic resources to achieve that. So there is no free time, at least if you want to really not watch it at all. So how do we... So we set off to measure this, but we thought, okay, let's do it in the classical regime first. Let's build the classical clock, which can be very susceptible to fluctuations. And let's see if this proportionality holds. So indeed, how did we do it? We had a mechanical resonator. You can see there a membrane in this case that was capacitively coupled to an LC resonator. So what we said was, okay, when the LC resonator would have a frequency when driven, right? And if we capacitively couple to an object that it moves, then naturally the resonance frequency of this LC resonator would be modulated by the motion of that mechanical resonator, and we would be able to measure displacement with really high accuracies. In the spirit of LIGO, really, right? But a lot tinier. So a cavity that actually allows you to measure displacements that are tiny. And on the other hand, what we could do is inject some noise, some synthetic noise, just to make the membrane shake. This is basically like effectively turning on the heater. We are basically elevating the membrane's temperature. So basically, in this experiment, what we wanted to do, and this is the whole spirit of the program, to actually make an experiment in which we can measure all thermodynamic quantities involved. So here, we had some, oh, sorry, wrong direction. There we go. We have some resource that is that noise, that heat that we are supplying. We have some dissipation, naturally, because the circuit would dissipate energy. And we can measure the signal of the clock. So here I will show you basically how the experiment looks like. That's our membrane. This is gigantic for the kind of things we do. Look, it's 1 millimeter. I will show you much tinier things. But it has it's 50 nanometers thick, the membrane. So fluctuations are quite important for the motion of these membranes. We can place them on top of metallic electrodes, as you can see. And that cavity, that it's an LC resonator, it's just made with inductors and capacitors. So there we have our circuit, and here you can see the cavity signal as a function of time. So what you are seeing there is the membrane just moving up and down. So basically, what we wanted to check, and what we did check, is that the accuracy that we can measure as the distance between ticks divided by the standard deviation of those ticks square is proportional to the Y noise that we inject, so the thermodynamic resource, and to the entropy production of the clock, meaning the dissipation of the circuit. So we could measure all of this because we know exactly the entropy production by measuring the dissipation. We know how much power of the Y noise we are putting in, and we could measure the accuracy of that clock. And of course, it's a terrible clock. Nobody will use this as a clock. Please don't, because the accuracy is really bad. Accuracy meaning, you know, if the clock does tick, 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 okay, but if your clock goes tick, 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 bad clock. This is a really bad clock. The accuracy is terrible. But that's not what we wanted to do here. Not a good clock. What we wanted to do was to show that indeed the accuracy is proportional to the entropy production, meaning that if you want an accurate clock, there is a thermodynamic cost, and that relation is linear. So our results show that there might be a universal relation, therefore, between the accuracy and the entropy production that doesn't only hold in the quantum regime, but also in the classical regime. So we published this paper, and we had a lot of attention because it's a really cool topic. So there are some very nice articles out there talking about keeping track of time, and you know. And here I have probably a question for Carlo, because they asked me, one of the journalists asked me, well, so I understand that if you measure time, are you telling me that if you measure time, you increase entropy? And I said, yeah, sure, that's basically what we're saying. And then this journalist went like, well, okay, but then it means that probably that the universe could die of an entropic, you know, by increasing the entropy, finally the universe would die. At this point, I was not so sure about this, but I said, well, maybe. And then, and then it was like, well, then we should stop measuring time. So what? Okay. So maybe Carlo can tell us a bit about this. I don't know the answer to this question. But okay, so now, but okay, so far we've been talking about classical fluctuations and so on. How do we take this to the quantum regime? So now it gets a lot trickier, because if we want to be in the quantum regime, we have to go cold and with very small objects. But in fact, we have a platform, and this program allowed us to build this platform in which we have a very, very tiny semiconductor wire. This is a carbon nanotube, which has around 2 nanometers of diameter, suspended between two pillars. And we have gate electrodes that allow us to control both the mechanical degrees of freedom and allow us to trap a single electron. So we have a single electron trapped in a system that can also vibrate. So we have a quantum element, and we have the piston. Now, one of the first things that we set up to do in this information as fuel program was to say, do these two things talk? Because if the electron and the mechanics go separately and they have nothing to do with each other, then definitely this is not a good platform to work with. What we want is that we have the equivalent of a volume with a single electron and a piston. So the piston has to make an effect on the electron and vice versa. So I'm going to show you that. And I thought that instead of listening to me for half an hour, which can be torturous enough, I would show you, I'll call some of the members of the group who have done different parts of this, and they would show you how far we got. But before then, I just want to give you some background so that you can understand some of the things that they would tell you if you're not familiar with single electron tunneling. So we can trap electrons, I said, in these devices. Now, you can think of them, for most of what we're going to show you, that these devices are like transistors, because there is a gate and there is a bias. And depending on those, we have current or we don't have current. So with this gate, we can stop the current or let it flow. It's just that we are so cold, and this is so tiny, that current doesn't flow really as many electrons, but we can really trap single electrons. So we have a picture like that one there, where we have some reservoirs of electrons and some discrete energy transitions. So that's what these quantum dots are about. So if we, most of the time, the current is actually blocked, because if you don't set up the gate and the bias to the right position, then these energy transitions are not allowed. So most of the time the current is blocked. If you pull the gate, you would get these transitions such that you have electron tunneling. So if you measure actually the current as a function of gate voltage, you would see peaks. Every time electron tunneling is allowed, the current flows. And again, you can change the bias instead and make these transitions possible. So something that you would see today quite a lot are these diamond-shaped regions. In each of those, the number of charges in the carbon nanotube are fixed, are n plus 1. But this means that we can trap one more charge, and we have control over every single charge in the carbon nanotube. So this is great. This is our quantum system. And something quite interesting is that we can, by plugging an AC signal there, as we did before with the membrane, it could be noise, it could be a coherent drive, we can make this carbon nanotube shake and vibrate. So we have our piston there. Now, big question is, do these two things talk? The mechanical degree of freedom and the electrons. And we have some evidence that they do. These are these diamonds that I was showing you before. But now what we have here is the same gate voltage. So the x-axis is the same. But in the y-axis, we have the frequency with which we move the carbon nanotube. And what you see is that at some point, there is it brightens. So what it means is that when the carbon nanotube starts vibrating, the current lights up. So there is some talking between the electrons and the motion. In fact, you can see every time a diamond closes, also we have a dip in the frequency, something that we call a softening. So apparently electron tunneling also changes the frequency of the mechanics, and this is great because this is exactly what we wanted, that our piston talks to our quantum system so that we can monitor the work done by the system by measuring the displacement in the carbon nanotube. So now Jorge would show you, in fact, that we understood this and how we understood it and what does it allow us to do.
The first thing we did in order to describe our electromechanical coupling was to observe, as Natalia said, the action of the electric current on the resonating frequency of the device. To do this, we obtain an analytical equation, an analytical formula describing what's the resonant frequency of the device for a certain current. This is that equation which appears in the upper part. This equation depends on a very important parameter, which is the electromechanical coupling, or the coupling constant, which is the letter G. This is the force that a single electron performs on the nanotube when it fills the nanotube. The force of a single electron. With this formula, we obtain in the experiment the frequency dip that Natalia describes. Here, these gammas are the tunnel rates. This is the intensity of the current going in and out the nanotube, the current of electrons. If we fit the Coulomb peak, we can extract this factor G, which in our case, it was about 800 megahertz. The point of this is that the coupling constant is of the order of the resonant frequency of the device. Therefore, our device is one of the first to be in ultra-strong coupling. This is the force of a single electron on the nanotube is huge. It's of the same order of the elastic constant of the nanotube itself. Okay. With this parameter, we jump to the second experiment. In this case, we will use the information we obtain, the model we obtain, to evaluate the energy required to perform operations on the current. This is, by driving the nanotube, we can modulate the current, for example, by taking an electron into the nanotube and emptying the nanotube to perform, for example, a computation. If I have a current, my nanotube is filled with an electron with probability 1/2, and it's empty with probability 1/2. If I drive the nanotube to empty the nanotube, I'm performing a Landauer eraser, which is in the heart of information theory, of information thermodynamics. Using our model, we can compute what is the energy required to perform a Landauer eraser in the experiment. This is what we do. We are preparing the paper, and it's related with the objective 2 of our work. And as you can see, if in the point 2, for example, nothing is happening with the nanotube, therefore, if I plot the amplitude of the oscillation of the nanotube, it's very large. However, once I'm going inside the frequency dip, I start doing eraser. I start driving the current. Therefore, my oscillation is very small, becomes smaller. And this difference between the large oscillation of the nanotube and the small oscillation of the nanotube is precisely the work required to do a Landauer eraser, or to do any kind of computation. Okay, and just to finish, I will explain the last experiment we did. The current of electrons flowing through the nanotube can create self-oscillations on the nanotube. If the device is autonomous, the current imposes the oscillations as a resonant frequency of the nanotube. This is self-oscillations. Self-oscillations can be directly measured. We can observe in the signal of the experiment the oscillations, which, as I said, is completely autonomous. This was already predicted in theory, and it was measured. What we did in the project was to pump on and destroy the self-oscillation. We proved that self-oscillations are B-stable. If the device presents self-oscillations and you pump the device, you can kill them. And if the device is off, has no self-oscillation, you can pump again to create the self-oscillation. The last we did is showing that self-oscillations are precisely B-stable. As you can see, just to tuning the device configurations, voltage configurations, you can find a region where self-oscillations are always stable, another region where self-oscillations are B-stable, but they are created by noise. Just the noise is enough, the fluctuations is enough to create the self-oscillation. And a region when we can start and kill the self-oscillations continuously. Okay, the next part is related with the spin, which Fede is explaining.
This is about essentially what I've done for my participation in the role of this program with Natalia, and it's kind of related with the idea of to say, can we learn something about whether is this useful work that we can extract from a coherent quantum system. So this is kind of linked with the idea to say, is a coherent quantum system sort of special compared to other thermodynamic system, and can we build a platform to study this effect and see if it's real or not? And so the idea is to say, really to try to use our nanotubes to create a system where we have a quantum system. In our case, we will use the spin, degrees of freedom of a single charge, And then obviously we need a battery, which is the carbon nanotube movement. This is analogous to the previous experiment Natalia showed with the charge, Natalia and Jorge. So the movement of the carbon nanotube will act as a battery. And then obviously we need heat baths. This is kind of a critical point for us at the moment. I'm sure there will be possibly good discussion about this because we're still working on what is a good heat bath for a spin. And the idea of our work here was really to follow along a paper written by Janet Anders and Kammerlander in 2016 that basically design a protocol where we prepare our quantum state, we do some type of operations, and we follow a specific set of external operation on the Hamiltonian of our system that kind of simulate a thermodynamic cycle to see, and then we obviously measure our battery to see if we can actually extract work from it. So the way this actually works more in practice is obviously we start from our carbon nanotube, and essentially instead of working with one quantum dot, we work with two quantum dots coupled together. For all means and purposes, Natalia and Jorge showed this beautiful diamond measurement. Those are measurements that come up from a single quantum dot. But if you have two quantum dots, your current measurement looks sort of like this triangle that you see over here. And what is important is because we can isolate individual charge, when we have two quantum dots, we can also access information about the spin of these charges. In particular, you can see that our current features that we have in this measurement can be kind of different depending on whether the spins that fill our quantum dot either form a singlet pair or a triplet pair, indicated like this. And specifically in our case, it means we have a certain current. We can measure current if our system is in a singlet state, and we don't if it's in a triplet. Now, this is quite useful because it allows us to measure the spin degrees of freedom, and it gives us access to a way to control the spin because we can do spin resonance, and we can see these lines, which essentially gives us a way to control this quantum system inside our carbon nanotube. And then the next thing we want to do is to add the mechanical degrees of freedom. So like we said before, we can apply radio frequency signal to our device. And when the carbon nanotube starts moving, we see strong switches in our current. And we are sure that these are mechanical features because we can tune the mechanical frequency like a guitar. If we change the gate voltage, we increase the tension in the carbon nanotube because the electric field pulls from the gates, pulls the carbon nanotube. At the end of the day, is a conductor, so it pulls it, and we can tune the mechanical frequency like if it's a little guitar, and we can follow this up in our measurement. And so really, finally, the whole idea was to look and study this special regime where the frequency at which we control and flip the spin in our quantum dot matches the mechanical frequency of the carbon nanotube. And what we see here is that at the resonant condition, we have a splitting of the two curves, which again signifies that not only the charge and the mechanical motion couple together in this system, but also the spin degrees of freedom couples to the mechanical motion. And so really, this one, it's actually, well, again, we measure the frequency shift. In this case, it was 86 megahertz, so not ultra strong for the case of the spin. But in any case, we were able to look at this in depth. We even come up with a model. We know, for example, that this type of coupling comes from the strong spin-orbit interaction of this system, and we are able to look at this from a microscopic level and make very beautiful simulation about it. And really, this is the first step of something, more fundamental, which is the objective 3 in the program of Natalia, which is, can we measure work associated with the coherences of a quantum system? And just to conclude my part, as I mentioned before, we're working on a protocol. So now we know that the spin and the mechanics couple, so we know that our quantum system couples to the battery. And so the next step is, can we really start thinking about the proper thermodynamic cycle that we would do with this system in order to see and try to demonstrate if there is some useful work that we can extract from the coherences of the spin. And with this, I leave it to the next speaker, Sophia.
So my name is Sophia, and I'll be talking about second to last project, I think, if I'm not mistaken. So here what I'm going to be talking about is when, up to now, we have been talking about the sample. But in this project, we have the implementation of adding a heater, as you can see there. I hope that you can see with my gestures. So now when we have a heater, we can talk about having reservoirs at different temperatures. So here in the schematics, we can see that in the left side, we can have a more hot reservoir, and that hotter than the right side in a way. So when we have this, we can kind of start talking about engines. So very schematically here, we are able to define a heat current, a left side and a right side. And then since we have some kind of engine, we can define mechanical work, as you can see here. And we have been developing a lot of theoretical work behind this. And here I'm just going to show kind of our main results that we have so far. So we can define some kind of power. And in this power, I'm not going to get into details of the equation, but all I want to say is that in this power, we can show how this back action that Natalia was talking about, and Federico and Jorge and all my colleagues, we are able to enhance or show that the engine has some kind of effect due to this back action. Yes. And so with this, I hand it over to Natalia.
I hope you kind of enjoyed all the aspects of this. This is to wrap everything up in the sense that, okay, we managed to build this platform in which we have heat reservoirs at different temperatures, a single electron that can couple to the mechanics. We have spin degrees of freedom to have long-lived quantum states in which that couple to the mechanics in a way that we can measure them. We can have a direct probe of the work done by the system, so that we can really follow a thermodynamic cycle, and we did so with charge and with spin. So we did a lot in this direction, and we are very happy that with the progress we made. And also we have managed to open new directions of research. This is with a group of with these groups of awardees, which are Melbourne in particular, about the thermodynamics of learning. We also realized that our devices can help us understand what is the cost of learning for a machine. And this is some work in progress. I hope Gerard can talk a bit more about this later. But if you have questions, do let me know. And well, I mean, a bit stepping back, I wanted to say that the FQxI this program has managed unbelievable things. We got a really nice dilution refrigerator to cool down our samples to 20 millikelvin, so very expensive and very cold, coldest that anywhere in the universe actually. So that is super cool. In the process, I got my professorship. That was amazing as well. Thank you. And this was followed also by two big programs that this grant has facilitated. One is my ERC starting grant, and this flagship project, European. In this case, we are going to study more thermodynamics in the solid state, and this project is about thermodynamics of precision. So what is the thermodynamic cost of the thermodynamic limits of precision in different devices? So it has given rise to different research topics and very exciting things. And with this, I will finish. This is the summary of the things that we've done and that I have showed you today, and that I would be happy to discuss further. And this is the amazing team that you have met some of the people today. But a bunch of others that have not come today, and they made this a fantastic program. So, well, and thank you for listening.